Hello, this is AP Calculus Lecture 1.3b. I'm going to title this lecture Limits and Indeterminate Forms. Okay, so this is a situation where with the last lecture we had direct substitution. You could plug the number in and get an answer. That's not going to be the case here. We have to do some more work usually. So let me give you an example here. Let's say we want to take the limit as x approaches 0 of x cubed plus x over x. Now if we plug 0 in for x, we'd have 0 plus 0 over 0. Well, that's 0 over 0. Well, that's not an answer. That means this function needs more work. And we call 0 over 0 indeterminate form. So let's do it. Let me write a definition out, and then I'll show you how that you can manipulate this to get an answer. So limits that produce indeterminate forms just 0 over 0 may or may not exist. They usually do in this class. More work is needed to evaluate the limit. Okay, so let's do a simple example here. Let's say we have the limit. Okay, well, we're just going to do this example up here. Okay, we want to take the limit as x approaches 0 of x cubed plus x over x. Plug in, you get 0 over 0. Now, you have to do it this way. Rewrite the limit each time. But what could we do to the top? We could factor out of x. And I would have x squared plus 1. And then we still have our x on the bottom. It's just rewriting this. Now we can cross out that x over x. Hopefully remember doing things like that in pre-cal as we simplify things. As long as x does not equal 0, you must write this. Okay, you've got to write that. That's part of the answer. Rewrite limit every time. Limit as x approaches 0 now of just x squared plus 1, because the x over x is just 1, right? So we can now plug in 0 for x squared. That's 0 plus 1, so the answer is 1. So if I were to draw this function, what it looks like is a parabola. X squared plus 1 is a parabola with a vertex at y equals 1, but it has a hole right here. Okay, so that's why we got a 0 over 0, because it's undefined at x equals 0. However, we can take the limit of this and get an answer of 1. Okay, so we're going to do a lot of examples where we do more work. All right, it's really important that you follow this process. Write down the limit every time that you manipulate an equation, and also write down the domain restriction, or what I like to call the proviso. Okay, let's do some more examples. Let's evaluate the limit as x approaches 1 of 3x squared minus 2x minus 1 over x minus 1. Now if we plug in 1, I'm going to have 3 minus 2 minus 1, 0 on top, 1 minus 1, 0 on bottom. That's not an answer. It's indeterminate. Now you might remember in pre-cal we did these without the calculus. I had asked you to simplify, so that's what we're going to do. And if you see a trinomial like this, a second degree trinomial with a squared, you want to think of, how can I manipulate this? How about I try to factor it? So I'm going to go ahead and write the parentheses, put an x minus 1 on the bottom. Now, I'm going to give you a clue. One of these factors should be x minus 1. Excuse me. I don't know why I wrote plus. X minus 1. Otherwise, the bottom won't cancel out. So now, let's take a look. How about 3x plus 1? Let's see if that'll work. So if I FOIL this back out, I've got 3x times x, so that's 3x squared, plus x minus 3x, that would give you the minus 2x. Remember, we're FOILing here. First, outside, inside, last, just to check. And then 1 times negative 1 would give you negative 1. So it FOILs back out to that. You factored it correctly. Now we can cross out the x minus 1 as long as x does not equal to what? 1, because that would make the denominator 0. So now we can rewrite this as the limit as x approaches 1 of just 3x plus 1, because that pesky x minus 1 is now canceled out. You can plug a 1 in for x, and that's just going to be then 3 plus 1, and the answer is 4. All right, pretty cool. We had to factor and then FOIL. And you need to remember some of those factoring rules. You might need to get out that pre-cal notebook and look at the difference of two perfect squares, or the difference of two perfect cubes, those kind of formulas. All right, we'll talk about that a little more when I give the homework assignment. All right, next example, let's evaluate the limit as x approaches 5 of x squared minus 4x minus 5 over x squared minus 6x plus 5. Now if you plug in a 5, you've got 25 minus 20 minus 5, 0 on top. And then here 25 minus 30 plus 5, 0 on the bottom. So this thing needs more work. Well, you've got two second degree trinomials, so that is a clue that maybe I'm going to need to do some factoring here. So I'm just going to go ahead and write the parentheses. Okay, this top one will factor into, got x, I think minus 5 plus 1 will work. Let's FOIL that out real quick. X squared minus 5x plus x will give you minus 4. Negative 5 times 1 is negative 5. On the bottom, pretty easy factoring when the number in front of x squared is 1, xx. All right, and then how about, I wonder if minus 5 minus 1 will work, just eyeballing this. So that'd be x squared minus 5x minus 1x, that give you minus 6x, and then negative 5 times negative 1 would be plus 5, so that works. Now we can cross out the x minus 5 over x minus 5 as long as x does not equal to 5. You must put this. I will count off if you don't. So this is the limit as x approaches 5 of x plus 1 over x minus 1. Now we've eliminated the 0 over 0. I can just plug in a 5. That's going to be 6 over 4. And that would reduce to 3 halves. All right, pretty cool. Giving you some factoring practice there. Hadn't done that in a while. Okay, let's keep on going with more examples. Okay, let's say we want to evaluate the limit as x approaches 3 of x squared minus x minus 6 over x squared plus 3x plus 2. Now, I hope you can kind of see, the first thing you always want to do is plug in, because it might not be 0 over 0. And if it's not 0 over 0, then we have an answer. The bottom's not going to be 0. It's all plus. So doing the bottom, that's going to be 3 squared is 9 plus 9 plus 2. That'll be 20. And then on the top, I've got 9 minus 3 minus 6. That's 0. That's not 0 over 0. 0 over 20 is 0. So we have an answer there. We don't have to do more work. We just have direct substitution. All right, let's do another one. How about the limit as x approaches -1 of x plus 5 over x squared minus 1. Now you might think, oh, I've got a factor. That's the difference of two perfect squares. Well, again, let's plug in first. On the top, I've got -1 plus 5, which is 4. So this is not indeterminate form. It's not 0 over 0. -1 squared, 1 minus 1. We do have a 0 on the bottom. Okay, so this is not, 4 over 0 is not indeterminate. This is undefined. So this is does not exist, and it's fine to write on your paper or on the test, just D and E. So a summary of the kind of answers that you could get would be 0 over 0, that's indeterminate form. And that's where it needs more work. You might have to do some factoring, etc. You're going to want to simplify. You can have 0 over not 0. And in that case, the limit is just equal to 0. And then the third possibility, if you have not a non-zero number, not 0 over 0, that is undefined. So the limit does not exist. Okay, I want to do a couple of more examples so you'll have good examples for the homework of and remind you how you did this kind of simplification back in pre-cal. So we can do some more indeterminate forms and remind you of a couple of techniques that you did in pre-cal. So two more techniques for evaluating limits. That's not how you spell technique. Okay, the first one is the cancellation technique. And so when evaluating the limit of, this is a compound fraction. So these look kind of scary, but you were taught how to do it. How to simplify it down. last year. Sorry that my music stand holding my notes. I don't know if you can hear that through the microphone, but it's it's shaking a little bit. That's what that noise is. So compound fraction. Try to simplify the fraction. By finding the lowest common denominator. Okay, so here's an example where we might use the cancellation technique. Let's take the limit as x approaches 0 of 1 over x plus 1 minus 1 over x. So in this case, if you plug that 0 in, you're going to have 1 over 1, which is 1 minus 1, 0 over 0. That's indeterminate form. Okay, so what we want to do is, first of all, try to make this numerator into one fraction. So I'm going to multiply the 1 by a clever version of 1. And what would make sense would be multiply it by x plus 1 over x plus 1. The denominator here, that's totally legal. X plus 1 over x plus 1 is 1. So that's going to be the limit as x approaches 0 of 1 over x plus 1 minus x plus 1 over x plus 1 over x. Now I can put these two fractions together. I can do the subtraction because I have a common denominator. So we have the limit as x approaches 0 of, on the top, 1 minus, and I want you to put this part in parentheses because the subtraction is of both components, both the x and the 1. So 1 minus x plus 1 over the common denominator, x plus 1 over x. Now remember, this is the same. We have this x down here as multiplying this top fraction by 1 over x, so you can really bring that x up a level. We haven't canceled anything yet, but you have to rewrite the limit every time. If you don't do that on the test, I will count off. And you have 1 minus x minus 1. So I just distributed that minus sign over x times x plus 1. That's the limit as x approaches 0. 1 minus x, 1 and negative 1 cancel. So I just have negative x over x times x plus 1. Now this is what we did all that work for. That pesky x over x that's causing my 0 over 0 now cancels as long as x does not equal 0, because if x is 0, you'd have a 0 in the denominator, right? So you've got to write that. What's left? It's the limit as x approaches 0 of negative 1 over x plus 1. Now we can plug in. I don't have a 0 on top. So I'd have a negative 1 over 0 plus 1, which is 1. So that is negative 1. All right, a lot of work, but hey, it gets the job done. And we got an answer. And a lot of good algebra techniques that we practiced. Okay, let's do one more example, and then I'll give you your homework. The second technique is the rationalization technique. All right, we did a lot of this as well in pre-cal. One way to simplify a binomial that contains radicals is to multiply by its conjugate. Now, if you've forgotten what a conjugate is, I will remind you. But ultimately, it's just a clever way of multiplying by 1. Okay, let's do an example. So let's find the limit as x approaches 0 of the square root of x plus 4 minus 2 over x. Now, if you plug in 0, you're going to get square root of 4, which is 2, minus 2, which is 0, over 0. So that's indeterminate. So we want to get rid of this radical, and that's when a conjugate comes in. So I'm going to go ahead and multiply the top by its conjugate, but you also have to multiply the bottom by that. So that's going to be the square root of x plus 4 minus 2 over x times the square root of x plus 4 plus 2 over the square root of x plus 4 plus 2. Now that's just 1, right? It's the same thing. But when I FOIL this out, the radical will go away. So we have the limit as x approaches 0. So let's FOIL this. Our first, root x plus 4 times root x plus 4. The radical lifts, and you're just going to have x plus 4. Then the outside would be 2 times root x plus 4. And then the inside is negative 2 times the square root of x plus 4. So that was the point of the whole thing. And then 2 times negative 2, our last of the foiling, would be minus 4. All over. Now I'm not going to see that x right there. We're going to try to get it to cancel out, so I'm not going to multiply it out. I'm just going to write it like this: the square root of x plus 4. Usually you want to hold off on multiplying the bottom out, so you don't want to distribute that x. That's what I'm trying to say. So let's see what happens here. Well, the 4 and the negative 4 cancel. 2 times root x plus 4 and negative 2 times root x plus 4 cancel. That was the whole point. And all that is left, we take the limit as x approaches 0 of x, because everything else canceled, over x times root x plus 4 plus 2. Well, now we're getting somewhere, because now we can cancel out the x over x as long as x does not equal what? 0. Because if it's 0, well, that's not the answer. I don't know why but we need to write that down. As long as x does not equal 0. So when we cancel out that x, what's left on top is a 1. Over the square root of x plus 4 plus 2. Now you can plug in, because it's not 0 over 0 anymore. We've got a 1 on top. So we've got 1 over root 2. Excuse me. That'd be root 4 plus 2. What's root 4? It's 2. So 1 over 2 plus 2, which is 1/4. Boom. All right. So that's those last two examples, quite a bit of work. So pause the video if you need to as I erase this, and I'll give you the homework and see if there's any clues I need to give you on the homework. Okay. So the homework for section 1.3b is page 64, and it runs into 65 a little bit. 37, 38, 41, 43, 44, and 45. So 6 of these limit problems. All right, just looking over, I'm going to look over them real quick here and see if I need to give you any clues. So, all right, 37, 38 are like what we did for 41. 41 has the difference of two perfect squares, so you'll need to remember that formula. 43 also has the difference of two perfect squares. 44 looks like a radical. 45, another radical on that. So the formula, it looks like you're going to be dealing with the difference of two perfect squares, so I'll remind you of that formula. Tomorrow I think we have to do perfect cubes. All right, so x squared, you have the difference of two perfect squares all right, a squared minus b squared. That factors into a plus b times a minus b. All right, and I think tomorrow we're going to need the difference of two perfect cubes. So that I think is the only factoring formula that hopefully you remember from pre-cal and algebra 2 that you'll need on this homework assignment, and I will talk to you on the next video.